Okay, so I will also say that um, communication can also come through the chat if possible. And during the sessions, a raise of hand for questions is what we use to go around. And I will advise colleagues to mute their mics because we are recording unless you are speaking. And hopefully we'll be able to get through with less technical hitches. If you mute your mic, it will be very helpful. Okay, so let me use this opportunity then to formally welcome partners and colleagues to this meeting. Good morning, ladies and gentlemen. A very warm welcome to this online event. This is the virtual multiplier event for our 3D print design and build project. My name is Andy Ekere, and I am a professor of manufacturing engineering and the principal investigator for this project. So first of all, some housekeeping. You will see on the screen the agenda for today's event. So we are now going to be having the opening address. Before I do that, let me say that we have a morning session and then an afternoon session. In the morning session, we hope we'll be having 4 presentations, as you will see on that agenda, 4 presentations. The first one, which will be done by Fideline from the University of Wolverhampton at 10:30, followed by a short break. And then we have the presentation from Gazi University by Dr. Kusad, and the one by Maker from SAMC, followed by the next one, which will be by Bellyfield on the learning platform. And then we go to the afternoon session, and then followed by the question and answer and plenary. We have a couple of visitors from outside the consortium today. A special welcome from participants joining us from all over the world. This indeed is a very important topic, and we are going to be discussing the results of our project. Why is today very, very important? Today is very important because 3D printing and additive layer manufacturing is a key enabling technology for the manufacturing sector. In fact, for all sectors of the society. As you probably know, manufacturing is the sector that plays the most significant role in the economy of the European Union, and indeed the economy of all developed nations around the world. We can think of the Japanese economy, the American economy, and indeed the Asian tigers. Manufacturing is the key economy that determines the welfare of these developed countries. It is vitally important for the European Union, as manufacturing continues, unfortunately, to decline because of high cost of labor, that the European Union become more competitive to ensure that it can compete globally with the Asian tigers. I mean China, Taiwan, Malaysia, to mention but a few. So this calls for greater efficiencies in manufacturing, greater efficiencies in terms of prototyping and development of goods. So 3D printing, or additive layer manufacturing as it's called, is helping to transform manufacturing, and the EU has therefore designated 3D printing as a key enabling technology to stimulate productivity, growth, and creation of new jobs. Creation of new jobs. This project, funded by the European Union, is contributing to this agenda. So, unfortunately, whilst 3D printing is developing very, very fast around the world, and the services of 3D printing can be found in every sector: aeronautical engineering. It can be found in food production, in the medical field, as you have seen with COVID, the printing of the PPEs. So 3D printing is a transformative technology. However, there is serious concern that education at primary, secondary, and tertiary levels is lagging behind the technology development. This mismatch in terms of demand for skills and the supply of qualified graduates is inhibiting the adoption of 3D printing and additive layer manufacturing. And this is what this project is trying to achieve. So now, let me share my slides. Please, if you can allow me to share my slides, and I use my slides to explain the project and what the project have sought to do. So just give me a minute. Let me go to share my slide for the presentation. Okay, so as I was saying, my name is Andy Ekere, and our project is 3D printer design and build curriculum development and delivery. And we are being funded by the European Union under the Erasmus Strategic Partnerships Project. The website for our project is shown on the right-hand corner of this slide. And you will be able to find details of our projects there, but I'm going to run through the project very, very quickly. So this opening address is about a welcome, which I have done. You are very welcome. An overview of our project, the implementation of the project using the intellectual outputs, which is really work packages, the impact of the project and what we have achieved so far. And as I said a few moments ago, there will be a plenary session where we'll look at project sustainability and plans for the future. I have already talked about 3D printing and the importance. We have 6 partners in this project: the University of Wolverhampton, which is where I was based until earlier this month. I'm now with Liverpool John Moores. The second partner is Karabük University, presenting today, Gazi University presenting, both from Turkey, and then SAMK from Finland, Bellyfield from UK, and then US Mechatronics, an important partner that developed, specified, and developed a 3D printer as part of this project. And we are delighted to have all these partners on the project. And the aims of our project can be captured under these headings: enhance the quality and relevance of students' knowledge and skills in terms of employability and skills which I referenced earlier, improving opportunities for entry into advanced manufacturing jobs, enhancing learning through digital literacy, working with local schools in terms of outreach. I'll come back to that later on. Increasing awareness and attractiveness of careers in STEM, science, technology, engineering, and mathematics for school children. And then trying through this process of outreach to improve the gender balance in science and engineering. Increasing opportunities for the development of skills that are relevant to industry, the aero, auto, food, and manufacturing sectors of the economy. Those are the objectives. The budget for the project, about 264,000 euros. Project started 2018 and finishes this month, 36 months project. I have referenced the project website earlier, so you can get more information from there. So the project is implemented through through intellectual outputs or work packages, and we had 7 work packages, as you can see on this slide. There will be presentations on each of these work packages. Intellectual output number 1, of course, is the initial research. So we're not presenting on that today, but we're presenting on number 2, which will be done by Fadalin from the University of Wolverhampton, and then the others will follow. Okay, so that is how the project is organized. Schematically, you can see here in the diagram, starting with the first intellectual output number 1, which is the needs analysis. We did a couple of country needs analysis and reports for the UK, for Turkey, and for Finland, and that formed the basis for developing the content of the learning module, which we'll be talking about today. Then we use the ideas that we got from literature in terms of specifying a 3D printer that was then developed by US MECMEC under intellectual output number 3. Intellectual output number 4, to be presented by Gazi University, is the handbook and manual that will be used for the printer that is developed and also for the e-learning platform. And then we go to intellectual output number 5, which is really to do with the preparation of the learning materials that is used for the module, including the assessment methods for the school's competition. And then we'll move on to intellectual output number 6, which is, sorry, something has happened here. Not sure why I have lost control of. Can you still hear me?
Yes, we can.
Yes, we can hear you.
So my system has stalled, as tends to happen with these systems. Okay, it's working now. So intellectual output number 6 is the learning modules, and then intellectual output number 7 is the printer resource pack. I need to move very quickly now because we are falling a little bit behind. So what we have achieved from the project is listed here: national reports that was used for developing the learning modules in terms of the skills gap and the gaps in terms of training and use of 3D printing in the 3 partner countries, UK, Turkey, and Finland. Copies of those reports are available on our website. And then development of the e-learning platform, which will be presented by Billy Phil. Today, the curriculum for 3D printing at master's level that was put together for us by our partner in Gazi University, and then the training seminars that we did for teachers, mostly in Turkey and in Finland. Those are the results. And STEM outreach for local schools also took place in Turkey, lots and lots of workshops also in Finland. Those are the brief sketch of the outcome for our project. And the work in terms of outreach was done using the schools competition, which you can see here, schools competition with the local schools, in order to achieve a whole range of objectives, as you can see in the slide. So I am going to stop here, and then we come back to the impact of the project in the plenary session. So once again, welcome to this event. We are looking forward to sharing with you the outcomes of our project throughout today's session. I have literally gone through a whole gamut of information in very short time. So perhaps, Liz, if you can stop sharing, we go back to the agenda again so that I can reintroduce the presenters, and then we go for the first session. So I'll stop sharing. Are you able to get possession of the? Yeah, okay.
Can you see it now?
Okay, so I think we're a little bit ahead of time. That should have started at 10:30. So the first presentation will be done by Dr. Fideline Shiombo Magai from the University of Wolverhampton. Fideline is a chemical engineer, senior lecturer with the School of Engineering and the Faculty of Science and Engineering, and her other role is serving as the coordinator for outreach with our local secondary schools. She plays a vital role in terms of the STEM agenda, where we are seeking to rebalance gender coming into engineering, science, and technology. So Fideline will be presenting on intellectual output number 2, which has looked at the work we have done at the University of Wolverhampton in implementing the learning module. And we have done that at the level of the Master of Engineering degree program for the aeronautical engineering students and mechanical engineering students at the master's level. And it's a group project which we have done for 2 years. First of all, for the 2018-2019 year, and then for the 2020-2021 year. We have done that with a group of students that have gone through the process. So can you share your slide if you can?
Yes, I will try to share my slide. Let me see.
So while she's doing that, we have a couple of other colleagues from the University of Wolverhampton.
Can you see my screen?
Yeah, let me finish. They have been part of the implementation of the project at the University of Wolverhampton, and that includes the technical staff, Chris Chu, that has helped with the students in terms of implementing this project, and our PhD student, Ali Reza Islami Majid, who is here today. They have also been helpful, and behind the scenes, of course, the research project manager for the Faculty of Science and Engineering, Liz Flitham, who has been coordinating this project. So what Fideline is presenting is the work of several people. And thank you, Fideline, for stepping in today to help. Okay, over to you. You have more time than allocated. So
okay.
Okay, so once again, welcome to colleagues joining us from all over the world. The process for today is the presentations will happen. If you have enough time at the end of each one, we take questions. Otherwise, there's a question and answer session, which will come up at 2:30 today, when we can take questions from all the sessions. But if you have time at the end of each one, we can take a couple of questions and then continue. And then I implore you, please, to come back at 3 o'clock for the plenary session. We'll be looking at the opportunities for collaborative R&D and how we can sustain the work of this project beyond the funding period. So you're very welcome. Over to you, Fideline.
Thank you so much, Professor Ekere. Good morning, everyone. My name is Fideline Chembu Magaya, and I'm delighted to be sharing with you our work. As Professor Ekere said, I'm almost the presenter, and I'm honored to have that, to play that role. So this project is about 3D printer design and bio learning module. So the case study concerned the work done by the team at the University of Wolverhampton, in particular, the implementation of the group research project for MNG degree for the cohort 2018-19, 2020-21 academic sessions. The layout of this talk is as follows. Basically, it's divided in two parts. The first part is the context. So just put this work we have done into the context of the whole project. And the second part deal with the actual research projects, which encompasses two components, project specifications, and the assembly of a DIY 3D printer and dimensional accuracy analysis of the printed components. So design, or the 3D printer design and build-based research projects is a part of intellectual output number 2, which also form the building block of other intellectual output that Professor Ekere described before. The content is based on the result of the intellectual output number 1, conceptualization and need analysis. So where all the partners have actually done, like we call it 3D printing awareness and skill gaps analysis in Finland, UK, and Turkey. The main focus was in the area of aerospace, automotive, and food manufacturing industry. There was also a survey performed by Belifio, which analyzed the needs and in all these companies. So the 3D printing skill needs. The information from the national reports and the survey inform the design of the content of the module and the development of the learning, the e-learning platform. As you already know, and Professor Ekere touched upon this a little bit, 3D printing is really important and beneficial in education at all levels. Whether we're talking about kindergarten with small 3D printing toys, or in primary, secondary, and higher education. Here are just some examples based on the higher education skill required. The examples are just a few among many, but creativity, the excitement that when students work with 3D printing, just give them that wow, especially when students experience their project from the conceptualization or conception of the actual creation of the model and to the actual seeing the actual physical product. That experience and hands-on would enhance their learning experience. And during this process, students would come across lots of problems, and we would talk about some of those problems later on, which would enhance their resilience, their problem-solving skills. They have to be creative in finding solutions which contribute to their employability and entrepreneurial skill. Working through this project, through the 3D printing process, build, assembling, and analyze the accuracy of components, students will have the opportunity to achieve some relevant high quality skill and competency required in aero, automotive, and food and healthcare manufacturing sector, especially that 3D printing and additive manufacturing emerging technology with application in food and healthcare, especially, I just mentioned here a few examples, personalized food, personalized medicine, and medical devices. In manufacturing of a piece or parts, a quick prototyping in a manufacturing sector. So you see that 3D printing is highly used nearly in every sector. Now, you see that 3D printing, this is actually a code from someone, so I'm not taking ownership of this. So 3D printing makes it possible for every student to dream bigger and better. And you see when people dream bigger, they can achieve lots of things. Now, how, in terms of acquisition of those skills and competencies, how can this be done in practice? Our approach is through the use of project-based learning, as illustrated with this diagram. First, our student has to complete a project specification form, which is based on a literature review that allows them to define, select the title of their project. Then they provide a short introduction and identified 3 to 5 objectives. This then allows them as a group, remember that the form is completed individually, then to allow each student to be fully engaged and reduce. As you work with students, you realize that when you have group project, some students would enjoy the role of passenger. So to avoid that, the form is completed individually, then students meet to discuss and make and agree on their group research project specification. When students agree with their project specification, they then start implementing their project specification. Work together, but produce individual reports and individual presentation. This for the research project module. The learning outcomes is as follows. So the students should be able to formulate a research question with specific objectives, valid hypotheses. They have to demonstrate the ability to devise a sound methodology, devise and follow a sound methodology. They have to demonstrate the ability to apply research results in relevant industry and solve problems. They have to critically analyze their results at a master level to show that the level should be what we expect for a master student, with clear, concise and objective narrative. Now, how do we assess? The assessment is based on two main components. The first, which is the report, as I mentioned before, and the second, a presentation, oral presentation. The report is divided in two parts. The first is an interim report, just few weeks after the student has agreed about their project specification and on what they're going to work on. This interim report, which is only 20%, allows us to give feedback. For us, it's almost like a formative assignment. The 20% is on like an incentive. You agree with me that assessment encourage and enhance learning. So if we combine with appropriate feedback, we empower students to take ownership of their work or of their learning. So after that interim report, they will again work toward incorporate the feedback and work toward their final report, which will be 80%, and the total give the 90% component, report component. After that, they will do the presentation, that is 10%. The marking criteria designed to take into consideration the skills and competence, and also align with the learning outcome that we saw before. And this range from problem articulation to proper referencing the source. And you know that in 3D printing, one of the issues here is how to protect the intellectual property of either people or how a student would be working safely, and also learn to recognize and acknowledge people work as we developing quickly a prototype, and you can download a prototype also from a different website. So we have the creativity component, how innovative, how creative their idea or their thinking process. How can they analyze, critically analyze the problem, their result, and discuss with reference to the literature and to other available resources. The economic aspect is crucial. It has to be whatever they try to implement and to research on, they have to take into consideration the economic, the social, and environmental aspects. Project management skill, you see that they work as a team, and also they will have a team leader. And wherever they will go into industry, they will have to work as a team, and they will have to report to someone. So they have to also demonstrate and learn how to work with people and how to manage a relationship. And of course, safety, health and safety is paramount in any industry. Safety comes first. Now, let's look at what the first cohort has done, the cohort of 2018-19. Their aim was to specify and build a desktop 3D printer that is suitable for use within university or college laboratory setting. For that, to achieve that, they have 4 specific objectives. First, analyze the main type of 3D printer that are available for DIY assembly. Identify the main component of a desktop, because if they know the main component and their function, it would help them in the process of assembly and build or produce the component with the 3D printer. They have to examine the key criteria used in the selection process of a DIY 3D printer, and purchase a 3D printer kit. Test this, assemble this 3D printer kit and test that it's working as intended, and that can be used within a university laboratory or a college. Now, this specification inform what they come out as a specification for what they were looking for. This was based in the literature. The first criteria was stability. So we have stability. We run a 3D printer that is a Cartesian printer, preferable a metal frame, prefer to have a heated bed, and later on you will see we have an example of project work that they study the effect of the temperature of the bed, the heated bed, on the accuracy of the printed material. So in terms of accuracy, they were looking for the nozzle size between 0.4 and 0.1 millimeter, and a software that we can actually use that can consider any that is compatible with any software that we can download and use, and with any 3D printing system. The material to consider was plastic, and especially polylactic acid, because it's biodegradable and they can dispose easily without negatively impacting the environment. You see that through the design, they were environmentally minded, and the size it should be a size of a desktop printer, with the cost no more than £700. This is the picture of the Prusa 3D printer kit that they bought, which was close to the specification they want. And here is the final assembly of the 3D printer that student come out that a student made, and they test that the printing component, they use this cube to calibrate and check, and found that everything was working properly within 1% accuracy, which is acceptable for what they were doing, knowing that the accuracy of this type of 3D printing at industrial scale is around 0.15. Now, the second project for the cohort 2020-2021, they look at similar task, which almost what the other cohort did, but with focus on dimensional accuracy study of the printed components. So again, they analyzed the main type of 3D printer available, main component examined, and select the 3D printer that could be used in the university environment, build like preview group and test. Why accuracy? We know that when we 3D print, the size that we put into or the prototype size should be close enough to the size of the actual material. As this cohort was working during COVID lockdown, they have to adapt and work as a team virtually. So after producing their specification, as mentioned before, they purchased the Prusa i3 MK3S Plus kit. When the kit was delivered at the university, they have to choose a team member who took the responsibility to go to the university, collect the kit, and assemble. And the assembling part, or the assembly task, was done by the team leader with support from other members of the team through virtual MSc video conference sessions. So you see how students, for us, that was one of more interesting and challenging part of their project. But as a team, they managed to do that very well. You will see later on. So using again that video conference, they could print the component, discuss what they have to do, search in parallel. So people searching in parallel when the main person design come across a problem, the other would be searching on internet how to overcome. They brainstorm, and then they send the answer, and then they work together to assemble. Then they 3D print component and study the effect of the temperature, the nozzle temperature, the layer thickness, and the heated bed temperature on the dimension of the printed material. So they measure the dimension of the material using a vernier caliper, and then from that calculate the percentage error. This is just an example of what student did, and you can see here from this picture that the temperature 60 and 100 degree give less polished surface and edges. You can see here is like warping, especially at 60 degrees. And they found that at 80 degrees, the edge, the surface was better when compared to 100 degrees and 60 degrees. And also the accuracy or the percentage error in the length of the calibrated curve was 1%, which is okay, knowing that the tolerance for industrial FDM printing is around 0.15. So how students work as a team under the lockdown? As mentioned before, they have a team member or team leader who actually build the component, and other was supporting, searching information, providing idea, how to build. They have a Dropbox file where they will share all the project results and data, and they held a meeting team for the implementation of various tasks activity leading to report writing, but individual report as mentioned before. Each student also present the work, they contribute their contribution, and a reflection on how the project went and how they want to take that forward, what they have learned forward in their future professional life. To summarize, with our MN program and research projects, students have assembled, they have specified and assemble and analyze the dimensional accuracy of their printed material. They came across different stumbling blocks. For example, what I didn't mention is that when students receive the pack, some components were missing. And those missing components, they could either try to make it themselves as the university chip technician or technician to make the component for them, which will take less than a day, or contact the company and within the lockdown context and wait for 2 to 3 weeks to receive the component, which cleverly they decided to ask the technician to print the component for them. And they use that and it works. They used the component that was the missing component that was 3D printed by the technician to carry on with their work. They also come through a lot of issue as based on student reflection here. One said, or 2 to 3, if I remember correctly, it was a good learning curve as it was a brand new experience for the team. They didn't know anything about 3D printing. Instead of, they heard about, but they have never assembled or worked with a 3D printer. So it was their first time. So they learn through try and error. They have to search for information when they come across a difficulty. They assemble first time, and when they calibrate it, it was giving them a component with a bizarre shape, and they have to do it again until they find they produce the right material, the right component, the right piece of product. So they come across lots of difficulty, try and error, but also learn about teamwork and how good teamwork can allow them to overcome easily easily challenges, and also produce high quality work. And also they recognize one of the interesting points. They recognize especially the code 2020-21, when they have to rely on heavily on their team leader to build, although they were supporting virtually, and it was a video conference, so they can support and see each other and see how the printer is built, but they still rely on the team leader. So they recognize the importance. They were very happy with how their team leader managed the whole team and the project. So you see, it is evident from this summary and from what we cover so far that students learn lots of transferable skills that will be used in industry. They start, whether it's just a research skills, they start from the beginning with devising their specification, design, assemble, make products, analyze the products, check the accuracy, think about thought about safety. So they cover everything that an R&D a professional would cover. So they almost ready, and they are planning and to take what they have learned into their professional life, and will be readily employable in the area where 3D printing skills such as aerospace, automotive, food is highly required. And also with the transferable skill, they can work in any other industry. So thank you for your attention. Please don't forget to visit our website, the 3D printing print project website. The link, 2 links are here, either through the page, the main page, or our Instagram page. Thank you. Happy to answer any questions.
Thank you so much. Thank you so much, Fideline, for the presentation. I can see people are already very detailed. Okay, I believe we have a short break, but you invited questions, so I'm going to allow 1 or 2 questions. Any questions, observations, or comments from the audience on the presentation by Fideline? You can raise your hand if you want to raise your hand so I can allow you to speak. Okay. Otherwise, we'll have the question and answer session at 2:30 in the afternoon. Okay, you're getting thumbs up and no questions. Okay, so just to restate, we have several presentations. This is one from the University of Wolverhampton, which is on intellectual output number 2. We would have used the printer specified, designed and built by US McMec, one of the partners on the project. However, due to the pandemic and for this particular semester of 2021, the challenge of having transport restrictions meant an import license meant they couldn't send it to us and other partners, so we had to use Prusa again. The first year was inevitable because we hadn't designed and built, but this particular last session we were hoping to use US McMec. We couldn't because we couldn't order and send from Turkey to the UK. But the printer that was designed and built as part of this project is available for retail through US McMec. If any of the participants or organizations would like to buy a reasonably priced 3D printer that you can assemble and use in your home or your work, then you can contact US McMec. This is an advert for them. This project did lead to a design and build of a new printer, which is widely available now and commercially available in the market, built by US McMec with support of Karabük University and Gazi University, universities based in, partners based in Turkey. They will be presenting today and they will talk a bit more about that. So without any questions for Fideline, can I say thank you, please? And I applaud Fideline for the presentation.
Thank you very much.
We're going to have a short break, and then we continue. I think he says we continue at 11:15, and that presentation will come from Dr. Kusad Cesar from Gazi University, and he is speaking on the work that they have done as part of this project, intellectual output number 4. And we have had to bring this forward because of the absence of Levant Aydin. I think we had to change this. We will get a short break, or should we continue? Are you available to continue from here rather than taking a short break? Is that the way we do it?
I think we can continue now if everyone is happy.
I think so, yes.
Yeah.
Let me just take a few minutes to introduce my colleague, Professor Kusad. He is an associate professor, and his area of expertise is design and development. Kusad did his PhD with the University of Manchester here in the UK, and is now an associate professor, I said, with Gazi University, one of the top universities in Turkey. He has been very, very instrumental in helping with the implementation of this project. In fact, he was also involved very much in writing of the proposal. So Kusad, we look forward to your presentation, and we hope you will be able to present aspects of your work as I suggested earlier.
Okay, thank you. Can you see my screen now? Can you see?
Yes, I can. Thank you.
Screen? Okay, that's great. The brief introduction on the overall structure of the project has already been mentioned, I think. I will start with 3D printers in schools. As you know, access to 3D printers is now very easy, and the use of 3D printers in education has become very widespread. For this reason, educators worldwide need to act quickly to bring this technology to their classrooms so that they don't fall behind this trend. We know that 3D printers provide many benefits for both students and educators. We can talk about many benefits, such as increasing motivation and interest in STEM subjects, making learning much more easier, that's already covered in the previous presentation, and gaining the necessary skills for future professions in today's business world. With 3D printing, classical passive learning actually becomes active by bringing STEM subjects to life with classroom activities. Of course, many procedural difficulties will be encountered in the process of actively using 3D printers in the classroom and updating the curriculum. We have some activities such as within this project, the use of 3D printers in secondary education, the awareness and training of teachers, design technology teachers in adaptation to the process, and the provision of online education resources that they will need within this project, Erasmus project. It's actually more focused on university education, but also covers secondary education. In this presentation, I would like to talk about some of these activities and basic principles of 3D printers in general. If we start with a design, which is the building block or the first start point for a 3D printer, making an object with a 3D printer starts with the design idea. When you think about design, design touches all areas of our lives. When you look up dictionary meaning of design or search internet, there are various different definitions of what design is. Therefore, it can be said there is no very simple explanation. However, in order to develop a perspective on what design is, we can talk about the following concepts. You generally evaluate the design from 4 different perspectives. One is form, second is function, third is performance, and the fourth is cost. Each of these is extremely important in the design process. Depending on what you are designing, some may outweigh others, but all 4 play an important role in the design process. If you consider the concept of form, it can be said the form is a part of design process that appeals to the aesthetic understanding of people. In other words, the concept that come to mind when we say aesthetics are things like color, shape, texture, feeling. Therefore, it includes all aspects that people evaluate a product in terms of tactile and visual sense. Going to the function aspect, the second aspect is a function. Function is also very important, and it can be said it is more about an engineering in the product. Function is the design process in which we try to determine what the product is used for. And this is the phase of the design process that should happen very early on. We determine what the end use or end application of a product, and we need to incorporate this into early design process. If we give an example of this, what is the main function of a watch? It keeps track of time. However, simple wrist watches can also perform the same expensive function with sufficient precision. When you look at much more expensive smartwatches here, they do much more than just keeping track of time. So here we are defining the function. What are the extra applications we can use with the watch? The smartwatch seen in this example is now more of a mobile than a watch. It keeps track of time. This is just one of the functions of the watch. But there are many other functions in this watch. So being able to predict what functions people will spend money on is a critical part of the design process. Of course, as I mentioned, this is something that needs to be determined very early in the design process, so it can be included in the product development process. The third design principle was performance. Now, performance is not a term that means the same to everyone. For example, again, if we take car as an example, performance may mean fuel economy to some. For some, it may mean reliability. For others, it may mean acceleration. For a fourth person, it may mean traction advantage. So how do we use performance as a feature in the design process? What does the market segment of the car look like? Who are your prime customers? If we know who our buyers are and what they want, then we can incorporate these aspects of design into our product. So performance is actually a measurable product feature, but it's not the same for everyone. In the example of automotive design, this will have different aspects depending on the type of car you are designing. The last one is cost. This is an often forgotten, but it's very critical for the product to take its place in the market. You can make a product that meets form, function, and performance very well. As an example, again, if you take a car, a Ferrari will probably meet all the criteria of form, function, and performance. But how many people can afford it? Very little. So if you want to mass market your product and produce it in large numbers, cost becomes an extremely important part of the design. In other words, while making a design optimization, you should also consider manufacturability of the product. And in a sense, we design it in a way that will be easy to mass production in order to reduce the cost. Thus, therefore, these four factors are extremely critical in the field of design. Of course, there may be situations where some of these factors are more important than others. For example, in aircraft design, let's take a commercial passenger aircraft and a military aircraft design. When we think about commercial airliner design, it's an extremely competitive market. Price is very important, and besides the price, there are also things like fuel economy, comfort, etc. These are important secondary criteria. However, the competition here is usually on price. But in military aircraft design, performance is always at the top of the list. Price usually comes at the end of the list. Performance is much more critical here because it's a life or death situation. In other words, there can be very different approaches in design for products in the same category. There are things like things taken into account when you look at design as the core principle of product development. So if you go to 3D printing, that's the main aim of this project, and ask what is 3D printer. In fact, this is a term that has taken the name of 3D printer because this is taught as the 2D printing logic of computer printers, which works by spraying ink on a paper and moving it to the third dimension. In 3D printing case, we move it to the third dimension. We can say that it's a technology that we can easily transform the design idea in our head into physical object, just like we take a computer printout from a digital file. If you look at the production methods, what is the main? So we can ask what is the main difference between 3D printers and other traditional manufacturing methods. Production methods can be roughly looked at under three headings. These are shaping with the mold, where we pour the molten material into the mold that we give the shape of the object we want. And when it solidifies, we open the mold and take the part. Production by removing material, in which the region outside the boundaries of the object to be produced from this block is removed with the cutting tools. And finally, production in 3D printing case, production by adding layer by layer material. If you look at the history of 3D printers, we see that this technology was originally developed for prototyping products. That's why this technology is also called rapid prototyping. In other words, this technology is widely used to make a model or prototype, which is the first step to transform a design idea into a product. Again, from an automotive example, when developing a new car, clay models are traditionally made to showcase the car's shape, form, and function. This is quite an expensive process. It sometimes takes weeks, if not months, to design and build prototype. Of course, it's a new car made here, and it's a product worth the effort and cost. But for a simpler product we make, we still have to prototype it to see if it meets the design criteria, and this would be an expensive process using traditional methods. For the last 10 to 15 years, additive manufacturing technologies, which is popularly known as 3D printing, has been increasingly popular. These technologies can be used very effectively for small production runs, such as prototyping. In addition, the process is very simple compared to traditional production methods, and the process limits are independent of part complexity. In other words, you can produce anything you can design with this methods. So if you can design it, you can manufacture it with this 3D printing. Of course, it has some limits. Our department's industrial design engineering at Gazi University, we use this technology actively in our rapid prototyping laboratory. Students design innovative products and then convert them to the machine code and run the machine code with 3D printers. We will now talk about production, logic of production with 3D printing and the basic principles behind this technology. We will try to give a broad idea of what opportunities exist in this new rapid prototyping and 3D world. Of course, you need to transfer the design idea to computer using suitable softwares. CAD softwares. 3D modeling is the first and most important step to 3D printing. Although the type of program to be used varies according to each need, the most popular 3D modeling programs used for production with 3D printers are shown in this slide. In our technology design teacher training, we have trained teachers on Tinkercad, a web-based CAD software that you can run online from a web browser, and this is known for its user friendliness and ease of use. There are some well-known CAD softwares. Sharing of these free open source digital design files. This is shared by users all over the world, can be found through these websites. And you can see many of them over here. From these sources, it's possible to access STL formatted CAD files that can be printed directly from 3D printers for different course topics. And you can see many of them, many examples in these slides. And if you look at 3D CAD modeling types, we can classify them as a wireframe model, surface model, and solid modeling. 3D CAD models are, of course, a requirement for 3D printers. With surface models, more complex freeform surfaces can be created, however, mismatched surfaces can cause problems here. In general, solid models are preferred. In fact, parts cannot be produced directly from CAD model yet. The CAD model must go through a pre-processing stage. STL format is standard now. In this format, CAD model geometry is expressed by planar triangular crystal surfaces. So while we use STL, all rapid prototyping or 3D modeling or additive manufacturing, layered manufacturing, whatever you call, all of these technologies apply the layer-by-layer production method. It's the easiest method to define 3D shapes with complex internal structures and 3D shapes in a series of layers from a 3D CAD model. So it's easy to derive a slice data from an STL file. It's important to use enough triangles in the parts in STL files. For example, a cube model requires only 12 triangles, 2 triangles in each face. So this provides maximum resolution. On the other hand, sphere requires many triangles. This can be controlled with tolerance settings in CAD software. However, depending on computer features used in large models, processing time may be longer. So unnecessarily increased triangles can cause delay in processing time. So this is an example of a sphere CAD model. As you can see, when the number of triangles is insufficient, the resolution is insufficient, and the model is defined as a polygon surface. You can produce parts you design in 3D printers in layers. You produce it in layers. As we just mentioned, you first create the CAD model of the part you want to produce in the computer environment, and in the software used for production, we divide the model into thin slices parallel to the horizontal plane. Then, starting from the lowest slice, when these slices are added on one on top of other and produced separately, the part is ready to use after adding the last slice. After being created on a digital platform and saved in STL format, the created project is transferred to the 3D-dimensional printers control softwares. In this software, the part is divided into layers. The production plan of each layer is then made. There are various three-dimensional object slice programs used in the market. Cura object slicing program, which is the most preferred among these programs, and offered to users free of charge by an Ultimaker printer manufacturer. We have given practical demo of this process that mentioned in our training programs within the project. So here are some of well-known and used slicer softwares. Cura is at the top, and many other open source codes here, so slicer softwares. So if we give an example of 3D printing of a knee implant that's shown on the slides, after the CAD model is saved as an STL file, it's divided into slices in the slicing program. After this, for each of these slices, here we show only for one of the slices. The path that printhead should follow is created by the software. In the next slice, it continues by adding on the previous one. Since the production is done by adding the slices on top of each other, this technology is called additive manufacturing. We technically call each slice as a layer, so this production method is also known as layered manufacturing. There are nearly 10 different technologies in this production category, and they all produce with the same logic. The main difference between them is how these slices or layers are produced, and in different technologies, these layers can be in thicknesses ranging from 10 micron to 500 micron. Once the production starts, no operation intervention is required until it's finished. The path to be followed by the printhead is programmed from the very beginning. After the production of the part is finished, you can do some processing operations. This is sanding, painting, that's to remove surface dullness and roughness if it is required or if it is necessary. So here is a simple cutaway animation of fused deposition modeling. As you can see, the head moves along the planned path according to the layer information, laying the molten plastic in the necessary places. Here, only the head seems to move along the X and Z axis, but the depth of the part is actually made by the Y movement of the table. Here is a FDM manufacturing process with the head moving in X, Y, and table moves in Z axis. The print head, that's also called extruder, is placed above the table and moves in X, Y planes. The table moves in Z direction, Z axis. It means it moves up and down. A plastic in the form of filament is drawn into the head of the extruder and melted by heating in this head. It's extruded and in liquid form, but viscous liquid. It's poured into the table, passing from a small diameter nozzle. At the end of the nozzle is placed at the end of the extruder. As this molten polymer is ejected from the nozzle in continuous flow mode, the extruder head follows a pre-programmed path, as in the example shown for one layer on the previous slide. At the end of each layer, the plate on which the piece is made descends in Z direction by one layer thickness. By the way, the first layer generally needs to be made porous for easy separation from the table after the part is finished. Here we see a video for the fused deposition modeling. I can run it quickly. As you can see, the model is the designed model is loaded to the 3D printer software and printed without intervention of the operator. And as in traditional methods, there are some design rules here as well. In the previous video, we didn't see any support structures because it wasn't needed. But for many models that, or for many products that we will need some support structures. For example, the part shown in this slide cannot be made directly because there is no underlying material on which the next slice or layer will be placed after the part has produced up to the level of point A on the very left corner picture. Here the solution is to make the part with support structures that are not actually part of the model. This is done with process planning at the design stage. Support structures can be defined as a structure on which all layers can be placed. So this is a necessary thing that in 3D printing. Of course, since these structures must be removed after the part is finished, and to facilitate this, they are usually made with voids and weaker or not fully dense like the model. A general rule of thumb for supporting structures is if the angle of the model's surface to the horizontal plane is 45 degrees or less, support structure is needed. If it's above, it's not required. In the previous video, we saw the angle of the face model is more than 45 degrees. It's been designed without support structures. And if you look at the extrusion profile in FDM, the layers are determined by nozzle diameter, and the layer thickness is generally between 50 to 300 micron. This thickness value also determines the most precise tolerance in the vertical direction. This is XZ plane. Of course, the dimensional tolerance in XY can be as low as 25 micron. When a product produced with FDM is examined closely, a step surface like a stair step is seen on the inclined outer planes. This surface roughness becomes more pronounced in direction proportion in the layer thickness. The surface image of the layers 50, 200, 300 micron shown on this in this slide. This figure explains this situation. 50 micron layers is more smooth, and 300 micron layers is much more rougher. If a better surface is required, however, some post-process such as sanding and coating can be applied. If you look at the materials, the polymers polymers is generally used in FDM, and the polymers extruded in viscose paste form gives best results. ABS, acrylonitrile butadiene styrene, is the most used material. It's a petroleum product. It's light, hard material. It's widely used in plastic injection industry. It can be used at temperatures 20 to 80 degrees. However, it emits some toxic gas at high temperatures. For this reason, it can be risky to use this in closed environments. Its melting temperature is around 100 degrees. Another frequently used material is PLA, polylactic acid. It works more smoothly than ABS because it melts at lower temperatures, and it does not require heating the platform because of the less distortion problem. PLA is a starch-based. It does not pose any health hazard. It produces parts with much lower strength. So this is the disadvantage. Solidification rate is also slower. Operating temperature should not exceed 50 degrees in this case. Polycarbonate is also used with much better strength compared to others. In addition to this, a mixture of polycarbonate ABS containing the polycarbonate strength and ABS flexibility can be used in materials with improved thermal and mechanical properties, and many other materials is available for use. And some classification for 3D materials for different technologies are shown here. So low-cost 3D FDM machines, as you know, the patent protection period of FDM process ended in 2014. So after this protection is ended, the open source machine design and software sharing movement has begun. Low-cost FDM machines are then offered to users quite widely, either completely ready for production or as a kit containing all parts. It's very useful for students to learn the parts and also the parts and working principles of the 3D printer, as well as the assembly of the 3D printers that come as a kits. Here I will try to explain 3D printer parts and working principle on a Prusa-ready kit printer, which was made within the scope of our Erasmus project. The entire production, calibration, and application process with this printer is available on the project website as detailed video and is available for your use. If you look at the materials used for most of the 3D printers are actually ready-made machine parts. Simple bent or laser cut sheets, nuts and bolts, shaft, linear bearings, and some of the more complex structures inside can actually be 3D printed. Detailed information about the materials used is also available on the project website. The fact that you can produce your CAD design quickly and easily in a computer environment on this FDM 3D printer, this is actually due to availability of this machine to melt the material and edit to very precise positions. So this is called additive manufacturing. To do this in 3D printer, there are parts such as motors that positions the printhead, plastic used for the model, and extrusion head to melt the plastic and placed onto table positioned in horizontal plane. So, yes, machine construction starts with the assembly of outer casing and installation of stepper motors. Positioning is very important, as I said, in 3D printer or any other 3D manufacturing process. There are various motors inside 3D printer. These are called stepper motors and provide very precise control in the X, Y, and Z directions of the extruder head. The next step is motor shaft connections, coupling. Here, the Z vertical movement of the extruder is provided with two worm gears. This controls the Z direction of the head. Many manufacturers are making FDM 3D printers nowadays, and there are many different designs that manufacturers used. And in this particular design, the H-bot design is used. It's named as H-bot because it actually resembles the letter H. The extruder head is actually moved up and down by our worm gears, which represents the vertical lines of the letter H. And extruder, the next step is extruder and the table assembly. In general, there is one motor for each X, Y, and Z axis. In this Prusa example, the movement of our X motors is transferred to the extruder head with plastic belts, so that the extruder head can move in X horizontal and Z vertical direction. The movement of Y motor is similarly transmitted to the table with plastic belts and moves the table in the Y direction. With this axis, we can position the extruder head, and as I mentioned, positioning accuracy is very important. In general, the resolution in axis transmitted by belt and pulley is around 100 micron and slightly less than this in axis transmitted by worm gear or ball screw. Of course, the tension and flexibility in the belts that transmit the motor movement are important in determining the resolution. So this is the kinematics in prose example. Of course, there are different methods and designs in motion transmission. For example, systems where the table is moving in X and Y axis and the extruder head is moving only in Z. And systems like polar 3D printers and robot arm control systems are also available. If you notice here, there are two guide shafts in X and Z axis movement of the extruder. Although the precise and accurate motor is used for axis movements, we will need to provide structural rigidity to ensure axis movement accuracy. For this reason, these guide shafts provide structural rigidity. So we have two guide shafts, each for X, Y, and Z axis. By the way, there are two worm gears for Z axis. Essentially, these two worm gears and two guide shafts acting like supports. So our Z axis is the best supported axis here, and hence our Z axis is the most stable and accurate axis we can predict. Now, most of these 3D printers are actually controlled by an Arduino control board microcontroller. Arduino is a development platform. With this provides convenience for electronics and robot applications. In order to make this card suitable for the purposes of providing controls we want in our 3D printers, a specially developed expansion card called Ram's Shield is generally used. This card controls every axis, X, Y, Z axis of the printer drive. Another motor actually feeds our plastic filament into the extruder, so it also controls this motor. These stepper motor drives are inserted into appropriate slots on this additional Ram's board, which is seated on the Arduino control board. It also controls how fast the extruder will pull the plastic filament. When the machine software converts your CAD file to G-code, which is a standard coding format, which controls motors, it converts them into movements along X, Y, and Z axis. Finally, the temperature control of the table and extruder head is also done by this card. These simple control cards are very easy and cheap to buy. And so these entry-level 3D printers have become simple and straightforward actually with this, and anyone can make their own 3D printer. Another important control used in these printers are end-stop switches, which determines the limits of the axis. When the extruder head is shifted to the far left of the corner of the corner of the printer, and it reaches the end stop, it records this as leftmost position of the table plate. From this position on, this axis movement along the distance of certain axis is counted by steps of the stepper motor, and the position is monitored. Of course, this procedure will usually need to be recalibrated after each print. So using after the printer is assembled, this is used for printing as a tested with a test cube. As you see in the front, the scripts in the front of this slide used to level the build plate in the horizontal plane. In this particular case, our table bottom plate is glass material. As the extruder goes from one end of this table to the other, the distance between the table and the extruder must be maintained. This can be one of the most time-consuming but important collaborations in 3D printing. The plate you are trying to print on must be compatible with the head. This tray is also heated actually, so there is a heater under the bed that maintains an even temperature on the bed surface. This is important, so plastic does not undergo a significant thermal change when it comes out of the extrusion hand and adheres to the table. It must be kept at a relatively constant temperature or it will shrink and separate from the table. As the height of the part we are printing increases, the part may be cooled by airflow coming from sides of the printer. The 3D printer actually doesn't have any side plates to stop this airflow. It's completely an open system. Therefore, the most accurate printing is done close to the table, where the part is kept at a relatively even temperature. So when the part is small, this type of printer gives better results. The larger the part, the more important it becomes that the part is well designed and takes into account considerations thermal shrinkage in the plastic. Now, let's look at briefly at the way extruder works. There is a gear here that pulls the plastic filament down. The gear is connected to the dry shaft of the stepper motor. The plastic filament is compressed between the gear teeth and the opposite pulley and pulled down towards the extruder. The extruder head, or more widely known as hot end, consists of an aluminum block and a tubular body with a heater inside. The plastic is melted inside this tube, keeping the rest of the plastic actually solid. So this works like a hypodermic needle or a syringe, because as the new plastic is pushed over the molten plastic is forced out through the nozzle opening, and the resulting melt is released onto the build plate. In summary, a 3D printer consists of a head with three axes, position control, and a material or a filament extrusion capability. So this plastic melt spread extruder can be the extruder can be removed actually from the machine and replaced with a syringe containing melted chocolate or other liquid, which can turn this into food printer. So it works with the same principle. Or more complex situations, we can turn this into a system that prints with bio-printing, bio-inks, and biomaterials extruded from a syringe. So you can easily replace this particular printer for a different purpose. So this is a simple sample heart cells, blood vessels, chambers designed in a hole and printed on a bio printer. So it's said that you know, there will be some organ printers in hospitals in the future. So this is all for my presentation. If you have any question, I can try to answer it. We use these materials to educate technology transfer teachers, and these assembly projects has been implemented in the graduate and postgraduate projects. Thank you very much for listening. If you have any question, I can try to answer.
Thank you so much, Dr. Pusat. Selza, this is a very, very detailed presentation on the basics of 3D printing and the FDM process. So well done. I wonder if you have any questions before we go to the next speaker. If you do have, you can take one or two and then return back to the question and answer session at 2:30. Any questions, please? Yes, I can see clapping of hands and thumbs up with no questions. Let's say from Fideline and Mika. So we can return to questions if we have them at 2:30. Thank you so much, Dr. Kusad.
Thank you.
For the presentation. Very grateful for the work. So now we move on to Mika. If you release the sharing, please, so that Mika can share from some. Thank you.
Just a second. Can you now see my slides?
Yes, we can.
Okay. Yes, very good. So thank you, Professor Ekere.
Let me
And
introduce the next speaker again. Our partners in Finland, SAMK, have been very, very instrumental in this project, in implementing this project. Provision of the learning materials. If you go on the website and on Instagram, you see that we have quite a lot of exemplars that have been put together by this partner. And Mika is the lead for the project from SANC and also runs the Artificial Intelligence Laboratory. They are very active online. If you want to know more about them, go on LinkedIn. She has been absolutely brilliant, and you will tell that from her presentation, which is starting very shortly. I shut up now. Mika, over to you, and thank you for the presentation.
Yes, thank you, Professor Ekere. So good afternoon, or I think that there is still morning in England, but here it's afternoon in Finland. My name is Mirka Leino, and I come from Satakunta University of Applied Sciences, the west coast of Finland. And for us, it has been a great pleasure to take part in this project and get to know all the great researchers that we have got to know here in this project. So let me first tell you a few words about our university. So we are a medium-sized university here in Finland, but certainly very small university on a global scale, I think. Our staff size is just over 400 people, and we have nearly 7,000 students. We have more than 30 degree programs, most of which are in Finnish, but 13 of them are in English. And we provide university education in the fields of technology, business, shipping, nursing, social work, and the arts. Satakunta University of Applied Sciences is an industrial university because our region is a well-known industrial region in Finland. We do extensive research in almost every area where we teach. And we who participated in this project are, like Professor Ekere said, we are a part of Robo AI research entity where robotics and artificial intelligence are studied from variety of perspectives. And yeah, we have 4 campuses in Satakunta province, which is located on the west coast of Finland. Our main campus is in Pori, and the second biggest campus is here in Rauma. And then we have the arts campus in Kankaanpää and also a business campus in Huittinen. All of these are in about 100 kilometers area. Okay, after that we can go to the point that is our role and what we did in this project. Although we made a lot of materials and also designed materials for undergraduate engineering students, we were especially responsible for Output 5, which was materials and assessment methods for 3D printing schools competition. This output was implemented through several phases. The first phase focused on the precise planning of the competition package. It was largely based on discussions with both 3D printing companies and technology teachers in our region. And once we had planned the needs and framework of the competition, we started to produce teaching materials, then assessment methods, and then plan the competition implementation. Then the third phase included lots of structuring and publication of materials, instructions, and the description of the competition progress, which we published on the RoboAI website. And it was at that point, it was published in Finnish. And then we organized this kind of a multiplier event as we have today, and presented the basics of 3D modeling and 3D printing, the produced materials, assessment methods, and the progress of the companies to the local teachers. And then after that, the teachers began to use the video materials and instructions in their teaching and try to attract interested pupils to participate in the competition and make a 3D model of their own use for 3D printing in the competition. And in the end, the competition jury evaluated all the 3D models and decided on the winner, as well as on the honorable mention of the work. We published the results of the competition to a 100% teacher audience during our RoboAI week on Technology in Teaching Day. Okay, then we can take a closer look at the production of materials. We think that the discussions with the companies and the technology teachers were really important. They highlighted also the need to teach 3D modeling so that the pupils and students can model 3D printable pieces themselves. And for this reason, the first part of the teaching materials consists of the basics of 3D modeling, as well as various 3D modeling exercises conducted in a free teaching-friendly Tinkercad environment. We made the materials initially in Finnish so that the local schools could get to know them as quickly as possible and thereby get to participate in the competition. Later, we produced all teaching materials also in English. All these materials consist of 7 videos that introduce you to 3D modeling and 3D printing, as well as to learn 3D modeling in Tinkercad environment. Tinkercad is a web-based 3D modeling software designed specially for school children and students as their first 3D modeling training environment. We believe that with the help of these published videos, it's possible to do 3 different modeling exercises. And now I'll try to show you the first page. Just a second. Here. So this is the page which we published before the competition. Although this part here, this is about the results of the competition. But this is the page we published in Finnish, as you can see. So first we have here the competition progress, and then we have here, this is the presentation about the competition for the teachers. And then here are the materials, 3D modeling, and then these exercises on Tinkercad. And then the last video is about the 3D printing for the pupils. Yes. Okay. And here you can see the list of all those videos and also links to all those videos. As you can see, first we have like a lecture about 3D modeling, and then we have 4 videos for practical study of modeling in Tinkercad. And finally, you can watch and listen to a lecture on 3D printing, different technologies and examples of their use. So these are all meant for the schools and school teachers so that they can use them on their teaching. And the purpose of the 3D printing schools competition was firstly to consider whether 3D modeling and 3D printing could be tools of school kids' everyday life. In addition, the competition taught 3D modeling, familiarized with the principles of 3D printing and various printing techniques, and of course competed for the best ideas. And at the multiplier events, we introduced this competition roadmap to the teachers. So first the teachers used our online teaching materials and videos, open to everyone, to give the pupils possibilities to learn the 3D model and familiarize with 3D printing. And of course, teachers could do this at school, or they can give these links to the pupils and they can watch them at home. Then the teachers collected teams of 2 to 3 pupils and challenged them to think about how they could improve their own daily lives with 3D printed parts or products. And then when they had their ideas, then the teams designed and 3D modeled their part or products. And when the 3D models were ready, the teams presented their output and their output's purpose to the jury in videos. They could have made a poster or a written text presenting their output as well, but every one of these teams wanted to make a video. So I think that it's really usual for kids of our days. And then the teachers sent 3D models and these video presentations to the competition jury, and it was in the middle of October last autumn. And then we released the results for RoboAI Week on November 9th last autumn. According to the multiplier events, many teachers were interested in the materials, but they didn't dare to join the competition without experience yet. Fortunately, however, a few technology teachers dared to join, and 6 teams took part in this first competition. So we thought before that we would be glad if we have 5 teams participating, and we had 6, so we were very happy. And these pupils, the teams who participated in the competition, they progressed in their studies of 3D modeling and 3D printing, utilizing the materials and watching the videos. So they could use, once they had watched the videos on their classes, then they could use, of course, the videos again and again, so they can go there and check how was this done and what did that mean, and so on. And the pupils from the teams participating in the competition, they were 10 to 12 years old. So in Finland they were on classes 5 and 6. And then after receiving all the entries, the jury made an assessment from 2 different perspectives. First, the innovativeness and usability of the designed product or piece. And secondly, the success of the 3D model considering the size of the piece, the proportions, and the versatile use of the tools. And then something about the results. As I told, the results of the competition were published to a 100-person teacher audience during Robo-AI Week. And the winner of the competition was a team called Team Kartat. It's a Finnish word meaning that they have their own maps to do this. And Team Kartat included 11-year-old Kerttu and Kosti, a girl and a boy, from Kaaro Primary School from Rauma. And they designed this, and also 3D modeled, of course, this stand that could be used to place a mobile phone and a tablet at the same time. And here you can see the jury's comments on the winning work, and they were: the output is clearly designed for the need. It has an innovative touch, as both a mobile phone and a tablet can be placed in the same stand. And a variety of shapes have been used in the modeling, and they have produced a really functional, simple wholeness. And then the jury of the competition also awarded an honorable mention for the work that had been designed and 3D modeled by computer girls from Rauma. And they are both 11 years old and designed a noise horn, yeah, in which a mobile phone is placed and which then amplifies the sounds coming from the mobile phone. And the jury's comments on the honorable work were: the output radiates imagination. Noise horn is looking for a solution to make a sound of a mobile phone better without a speaker connected to it. Ideation and planning show an understanding of the matter, and with a small specification refinement, noise horn would have won the competition. So they had some difficulties with the dimensions of the noise horn, and that's why they didn't win. Okay, then in the last year of the project, we have focused our work in this output on designing methods for assessment of the lessons learned according to the materials aimed at 3D printing skills. We found that the most important thing in primary school technology studies is to sow the seeds of interest in technology. However, from a teacher's perspective, it's also important to be able to assess students' learning outcomes. The planned assessment methods were already used in the evaluation of schools' competition work, but we just did some enhancements and refinements after that. We defined that teachers should evaluate students' learning outcomes and their outputs from two perspectives. First, the innovativeness, creativity, novelty, and usability of the output. So how good and creative an idea a pupil has, and how well he or she has been able to produce and enhance the idea into a 3D model, and thereby a functional 3D printed piece. And how the pupil utilizes their ability in the creative process. Are the ideas, products, or solutions generated in the process of creativity are novel, viable, or even commercially valuable? And secondly, the other assessment perspective is the success of the 3D model, considering the size of the piece, the proportions, and the versatile use of the different tools. So then it should be figured out how well has the pupil got their work dimensioned in the 3D model so that the 3D print matches the desired piece size. And are the dimensions of the part correct, and does it work as intended? All in all, we can say that when doing the assessment of such learning outcomes, the most important thing is to note what the pupil has learned, where he or she has been successful, and what ideas he or she has received. When using 3D modeling tools and doing 3D printing, there is not just one right way, but many different methods can achieve the right result. So if a pupil has not completed something, it's a good idea to think about how to complete it and not focus on what the pupil has done wrong. And these are the methods that we have tried to share with the teachers also, and they also think that the assessment done so that you just check what the pupil has learned and how much she or he has learned. It's really important in this kind of technology subjects. And finally, I have to tell that that here on our region, many schools have started to use our materials in technology teaching of 10 to 15-year-old pupils. And we have published a page with all the materials that we have done here, but also the entire semester's teaching. I'm not sure if I was. Can you still hear me?
Yes, we can.
Okay. Yes, yeah. Okay. So to organize so that the teachers can organize the entire semester's teaching, so that when they have 2 lessons per week, so this material is good for the whole semester. And now I try to, it's here. So here we have something about materials, and to whom they are focused. And then this is the first time, okay, everything in this is already also in Finnish, but this is the first lesson and the second lesson, so 2 hours lessons each time. So the second time, third time, and there is what should be done.
Excellent, excellent.
Yeah, so I hope so. I hope I was able to convey to you thoughts on the importance and possibilities of such materials.
Yes, I think we are grateful for the work you have done with Jonas and Tommy and the team, just to mention a few of your partners. Great presentation and symbolizing the work you and your team have contributed to our project. We're very grateful. And we have a worldwide audience today. So I'm going to say this before we continue. In addition to participants from the partner countries of UK, Finland, and Turkey, we have participants from France, from the US, from Singapore, Denmark, and Italy. It's not easy to tell the others because their email addresses are generic, but just looking at the emails from partner organizations, we have quite a good following today. So I'm hoping that the LinkedIn message I sent a couple of minutes ago saying, come and join us. There is a great meeting happening online at the moment. So thanks. Do you have any questions for Mika and her team before we continue? Any questions, observations, or comments, in particular from the external audience? If there is none, then I'm going to suggest we actually have a break. A cup of coffee will be helpful, isn't it? We have a break now.
Yes.
And then we can return for, let's say we return in 10 minutes for the next session, which will be done by Krishna. Krishna, is that all right?
Yeah, that's fine.
We didn't have the break we should have had earlier on, so people are now itching for a cup of coffee, and I hope everybody returns in 10 minutes, and then we can continue. Thank you so much for those who are joining us from outside the partnerships, in particular the colleague from the National University of Singapore. You can just don't go offline. You can stay online and join us in 10 minutes. Okay, so thank you so much. We'll see you in 10 minutes time.